Good afternoon. My name's Mark. I work on Java. Still. So this is a talk about the modular Java platform and Project Jigsaw. If you've been around DevOps for a while, you've heard talks with this title before. This talk is going to be different than the ones you've heard before. So what I'm going to try to focus on today is, rather than talking about a specific solution to a bunch of problems in the general space of modularity, I want to focus on the problems that we're seeking to solve by pursuing modularity. It's been my experience, our experience, that in this space, talking about a particular solution, it's kind of like when Brian talks about language syntax. People will get really focused on the syntax and the details, and they lose sight of the problems and relevant techniques. So today, let's just talk about the problems, and I'll leave a lot of time for questions, so we can actually have a discussion. Because part of my purpose for being here is I'd like to hear from you what it is you think the important problems to solve around modularity are. So here are three big goals for modularity. One is scalability, scaling the platform down to small devices, not just devices like the Raspberry Pi, but things that are even smaller. Improving performance of both code in the platform and application code, and improving platform security. As you might have heard, Java security has been in the news over the last year and some, and it'd be good to be able to improve that too, and we have some ideas which I'll discuss. Okay, scaling the platform. So small embedded computers have just gotten more and more powerful over the last, forever, right? Moore's law gives them more and more transistors, and they're still limited by power, and they're still limited by storage, but they can do an awful lot. This is actually a fairly old BeagleBoard-like thing. It's got an ARM processor and a quarter gig of memory of RAM. This thing is perfectly capable of running a Java SE class VM. You don't have to limit yourself to the really teeny Java ME, limited VM that doesn't have as many features. So the thing about devices like this is that their storage, their static storage, is still fairly limited. And the budget for static storage is a big part of the budget for the overall device. And when you're configuring one of these devices that you're going to use in a production run of 100,000 instances of whatever product it's embedded in, you care about spending another $1 or $2 on non-volatile memory that you might or might not use. So it'd be nice if you didn't have to carry around the entire JDK if you're not going to use the entire JDK. And of course, the common case is that you're not going to use the entire JDK. So that's the thing about Java SE, right? Is it's a monolith. It's always been specified as this huge, enormous thing. It's always been implemented as this huge, enormous thing. And the only real variance in most implementations is, you can get the entire JDK, which has the compiler and some developer tools and all the rest of it, or you can just get the Java runtime environment, which is somewhat smaller but still kind of big, right? The minimal JRE on as it happens for Oracle's Linux ARM build is 54 megabytes. Ew. Well, that's kind of large. So we've taken a first step towards solving this problem in Java 8 with the introduction of what we've called compact profiles. So this is kind of a preview, a down payment on true modularity, but it actually solves some important use cases. So the idea of compact profiles is to layer the platform, divide the platform into logical layers. One builds on top of the other. And if you're lucky and you only need stuff that's in a lower layer, then you don't need to include the entire JRE in your embedded solution. So at the core, we've got sort of the kernel, base, whatever you want to call it. Compact 1 is the smallest profile that exists. And in our Linux ARM build, that clocks in at 11 megabytes. So that's a lot smaller than 54, right? Layered on top of compact 1, we have, logically enough, compact 2. Compact 1 has all the core stuff in it. It's got Java-Lang object and Java-Lang string and IO and NIO and util and whatnot. Full support for Lambda, by the way. If you want to use Lambda, everything you need is in compact 1. Compact 2 adds JDBC and RMI and JAX-P, and it clocks in at about 16 megabytes. So it's a little bigger. And then compact 3 is between 2 and the full JRE, and that adds instrumentation and authentication and the compiler API and JDBC row sets and digital signatures for XML and preferences. I guess somebody uses preferences. And then what's left for that outer layer, which you might call compact 4, but is actually just called the JRE. Oh, sorry, compact 3 is 30 megs. What's left in the outer layer is the rest. So there's crypto, Corba, somebody needs Corba. All the desktop stuff, that's one giant module, contains Swing and AWT and 2D. The Nashorn JavaScript engine, JavaFX8 is in there as well. So the layered platform is definitely a step forward from the big giant monolithic platform. At least there's some flexibility. And if your application only needs the stuff that's in compact 3, then you get to save a significant amount of static storage. You just install compact 3 on your device rather than the entire JRE. This is still kind of limiting, though. Right? There's plenty of applications that will not be able to get any advantage out of this scheme. If you have an app that needs, say, JavaFX and RMI and Nashorn, well, you're stuck carrying along, Corba and the desktop APIs and everything else because, sorry, bub, you need to install the full JRE, and that's just the way it is. So, how do we get to, from this to a better solution? Well, the answer, of course, is we divide the platform into a finer-grained set of modules and have a richer relationship between them than just simple layers. So let's look at some more modules. The layers still correspond to the profiles. I've added in some finer-grained divisions. There are also some additional things that come in because they're part of the JDK, so we can consider those as modules as well. So, dev tools, for example, would contain Java-C. Now, the thing about having modules is the relationships between them are much more complex than layers. You can't just think of this simple layering model. Any particular module is, in general, only going to depend on 1, 2, maybe 3 others. Usually not that many. So we have to replace the simple, easy to understand layered solution with something more complex, and that is, of course, a graph, a directed graph. Fortunately, it is an acyclic directed graph. For people into graph algorithms, strictly speaking, this is the transitive reduction of the actual module graph. If I showed you the actual module graph, it would be an incredibly dense slide, and this slide is dense enough as it is. So what defines a module? Well, it's essentially a set of packages, of API packages, whatever API packages are exported by that module, and dependencies, the arrows in this diagram. So one thing that's important to point out is the base module, this guy right there in the bottom in the bold. That's the one module you always have to have. So that has a virtual machine in it. It has Java-Lang object in it. The very core of the system, what's needed to boot up. It turns out it's a little bit smaller than compact 1 in the Linux ARM build. I think it's around 10 megs, maybe a tad smaller than that. So once we have this nice module graph, we can have a much better solution to the scenario I just described. If we have an application that needs JavaFX, and it needs RMI, and it needs Nashorn, all we have to do to create the minimal JRE for that application is compute the transitive closure in this graph of what other modules are needed, and everything else we can throw away. So what's in the transitive closure? Well, RMI is going to bring in TLS, and it's going to bring in logging, because I guess you need logging if you're going to do RMI. Nosworm is going to bring in the scripting API, and everything else is just irrelevant, how it goes. So knowing this about the application, we can now build a custom JRE that just contains this stuff and will be, of course, way smaller than the full 54 megabyte JRE. So how do we actually deliver and build this newfangled JRE thing? So our answer for that is a new kind of artifact. We call them JMods, Java module files. We couldn't just use jars as they stand. Jar files don't have, well, they don't have any standard way to handle native code. And if we just started using jar files and stuck native code in them, they would be pretty confusing jar files, because in most cases, they wouldn't work in the way that you expect jar files to work. And of course, a big chunk of the JDK is a bunch of native code. So we have to have a way of handling that. A product like the JDK also has requirements around configuration files and other things that you need to track that aren't really accommodated very well by the jar format. In our current prototype, JMod files, well, the easy thing to do was just use the zip API, which was what we did many years ago, and that created the jar format. But it's different than jar, and kind of intentionally so that they don't get confused. So we can deliver the JDK as a pile of JMod files. Now, to actually use that, you want to do something to it. You want to assemble just the ones you need and create what amounts to a custom Java runtime environment for just your application based on the transitive closure of its dependencies in the module graph. So we need a tool that will take a bunch of code in JMod files and transform it into a bunch of code in an executable format. So what should we call a tool that transforms code into code and connects code together? Compiler? No. Executable code into executable code. A transformer? A linker. Thank you very much, sir. You win the prize. Yes, it's time for Java to have a linker. Every other respectable platform has a linker, so let's have a linker. Well, not just for that reason, but because it actually solves a problem. So we prototyped this new tool called JLink. Takes a bunch of JMod files, constructs an image. How do you use it? Well, it's a simple command line tool. You tell it what modules your application needs. It goes and finds them in a default location, or you can tell it where to find the JMod files. And you tell it where to put the result. And then out pops a JRE in the end. You can say, JRE bin java -jar, my application .jar, and your app will run on the custom JRE built just for it. Now, to make development easier, this new -mods flag is also supported by the JavaC compiler. So when you're developing your application, you can tell the compiler, I want my application only to use these modules. So please configure yourself so that when you're compiling code, if my source code tries to refer to something outside of these modules or outside of the transitive closure of these modules, please throw an error, because I don't want to be confused about that. Similarly, to help development, we support the mods flag on the Java launcher. So if you have the Java launcher on even the full JRE, but you want to test out an application that's only supposed to use a few modules, you can tell the JRE at startup time, only configure yourself with a few modules, pretend the rest don't exist, and let me run my application in that environment so that I can debug it without actually having to go to the trouble of creating a custom JRE for that purpose. So basically, we've got the linker tool to create the custom runtime, but we're also trying to maintain the fidelity, having the same behavior of a custom image, the same behavior at compile time, and the same behavior at runtime with a generic image. Okay. Performance. So in the Java world, historically, performance has really only been something that we think about at runtime. In the very early days, before there were good JITs, there were people who tried to optimize bytecodes and do inlining on class files and spit out new class files, and in desperate situations that was actually sometimes an okay solution. But with the advent of good JITs, it's class files they're handy compiled artifact. They are directly executable, but JITs are very good. They can do all of this fancy stuff at runtime. But there are still there are optimizations well known in the literature that are just too expensive to apply at runtime. In a JIT environment, you're always constrained by, well, the JIT is running alongside the application. You don't want to interfere with the application too much, but sometimes you need to do some analysis, and it's a whole complex set of trade-offs. It's amazing the amount of engineering that goes into these systems. Yet there are techniques we'd like to apply that would just be completely infeasible in that kind of context. These are generally whole program analysis techniques where you look at much more than a single class or a few classes in a class hierarchy, but you actually look at a big chunk of the program, or if not, or maybe the entire program. And these are optimizations that you wouldn't dare try to do at runtime, but maybe you could do if you had a build or at build time, or maybe at an install step. So, what are some examples? One is fast class lookup. If you look inside a modern VM at the obscure and very clever tricks used to optimize lookup on the class path, it's fairly impressive. Think about the class path. It's a sequence of named jar files typically. Each of those jar files has an index that's stored in a not particularly efficient form. So if you're talking about a URL class loader, you look for a particular class on a class path, you go look at the first jar file. If it's open, then some of it's cached. If that fails, then you go to the next jar file. Maybe you have to open it because it wasn't open before. And you keep going down the line. It's a linear search. Now, there's some things you can do to optimize it. But if we have all of the classes from the JRE and all the classes from our application, we could do way better than that. Right? We could compute, for example, we could pre-compute a single B tree that would let you look up any class in, for practical purposes, constant time. We can do aggressive inlining. Brian Getz, when he did his Lambda under the hood talk a couple hours ago, mentioned various techniques for optimizing lambdas. One that he didn't mention, but which he has been pestering me about, is doing aggressive inlining in this linking phase of the creation of lambda bodies, lambda capture and all of that. And this is actually a fairly simple analysis. Once you have the relevant classes to hand, it's not difficult to look across them, and even sometimes inline code from platform classes into application classes. We actually have that opportunity if we can look at the entire program. Another one is ahead of time compilation. There have been various experiments with this over the years. Certainly at Sun and Oracle, we've looked at this every few years. Is it time to do ahead of time compilation? Ahead of time compilation is good for a couple of things. One is it can really help application startup, which is important not only on the client but somewhat surprisingly on the server. Another big thing that ahead of time compilation is useful for is devices that have strict policies around them about not including JITs. Another possibility is JVM-specific memory images. So both Hotspot and IBM's J9 VM have the capability to read in a bunch of system classes. In J9's case, they can actually do this with application classes too. Read in a bunch of classes, parse them, create the VM's in-memory data structures, and then write that to a file. And then once that file is written, to start up the VM again, you just memory map that file into memory using mmap or the logical equivalent. You need to patch up some pointers and stuff because it might have wound up being mapped in at a different address than it was before. But now you don't have to spend all the time needed to parse those class files all over again, and you can get a significant improvement to startup. Now, in Hotspot, we can only do that right now for system classes. If you hack around with the boot class path, you can do it for your own classes. With J9, you can actually do it with application classes as well. It requires a bunch of kind of obscure product-specific command line flags. Wouldn't it be nice if we had a standard way of talking about this kind of optimization? Now, a final optimization that's interesting, and this gets pretty radical, is, well, gee, if we can look at the whole program, we could do static analysis, and in cases where we can prove that a method or a field or a class is never used, we can just take it out. Yeah, if you're familiar with, if you're an old Lisper, you know that this is called a tree shaker. Very old idea. You take a body of code, think of it as a tree with a bunch of leaves on it, some of which are loose. You turn it over and you shake it, and all the useless leaves fall out, and then what you're left with is just what you need. This kind of really aggressive trimming is, it's not for everybody. It's a little bit risky. It's often not going to get you very much because your static analysis is going to have to be conservative. If you give it a body of code that uses, even in just one place, class.forename, then unless you can infer things about how that class.forename is invoked, then you have to give up because you have to include everything because you don't know what that class.forename might try to load. But for limited applications that are going into a limited environment where you're never going to use reflection, this can actually buy you quite a lot. So, how do we box this up? How do we make this something that people can use? Well, the answer is, well, we have a linker now. Let's generalize the linker. So we can generalize the linker in a couple of ways. One is, rather than only consuming JMod files, which are intended primarily for the JDK itself, it can consume application classes, as in the form of jar files or even directory trees full of class files. It can consume those, create a custom image that might not even have a regular Java launcher in it. It only has a launcher for the application itself because that's all the image is intended ever to do. JLink can also create the custom JVM image, the big memory mapped structure that will save a lot of time at startup. It can also create, if you want them, it can create fat jars, although not if you have JMods with native code. And it can also be the tool that is used to transform class files into JMods to actually build the JMods themselves. And this is how we intend to bootstrap the modular JDK build. In terms of the command line, well, we just extend JLink in the natural way. We already have the mods option. Now we add a class path option. It will consume classes from both the JMod files that it finds that correspond to the modules specified here, and it will consume all the classes in app.jar and whatever other jar files you give it, and spit out a highly customized JRE. And you can then invoke that. There'll be, a single launcher in it to launch your app, and that's your app. You can take this JRE, bundle it up in whatever way is appropriate for your target environment, and ship it off. That's the whole thing. We can also use JLink to create a JVM specific image. Just as an example, I chose the file extension .jai. Don't hold me to it, just an example. And then you can start the VM by giving it that image, and everything it needs is right there. So it's very fast. So I've expressed the linker here in terms of kind of the obvious Java-style command line API. Our intent is actually to have an actual supported JDK API for this, so that you can invoke the linker from other kinds of tools, whether it's your build tool or anything else you care to do. We're also thinking that the linker should have a plugin API. I mean, these different kinds of optimizations, each one of those could be a plugin to the linker. Kind of like if you think about annotation processors in Java-C, it's a similar sort of thing. A linker could have a number of optimizer plugins available to it. You could tell it which optimizations you want to apply. The plugins will need to specify, which kinds of optimizations they have to come before or after, and things of that nature. But this would give us a very flexible tool that can be extended, really by anybody. So an important thing to note about linking before I go on is that linking is optional, right? I'm not suggesting that the whole Java development life cycle of everybody should change and you should always have to link. No, no, no. You can still take your jar files and stick them on a class path and run them with the regular Java launcher, just like you have for 18 years. But if you want to get some of these benefits of a custom runtime, of some of these optimizations that are infeasible to implement at runtime, then JLink could be a very useful tool. Now, as is often the case, there is no pain without gain. To enable some of these optimizations, we need to change the structure of the Java runtime image. In particular, we need to take away a couple of things that a lot of people are comfortable with. rt.jar and tools.jar, two files that you will find certainly in any OpenJDK or Oracle built JDK, and I'm pretty sure you can find them in IBM JDKs as well. These are going away. These are going away because they're actually a horrible representation of the information that a virtual machine needs at runtime. They were convenient for many years, they've served their purpose well, but it's time for them to move on. In fact, we're contemplating changing making other changes in the structure of an installed image, at least for OpenJDK derived implementations. There'll still be a bin directory. We're going to move editable properties files up into a conf directory so it's clear which files you might actually conceivably edit and have reasonable expectation of that working, as opposed to files that are really part of this implementation and you shouldn't touch them because if you do, something is probably going to break. We're going to move the extensions directory up to the top level for a similar reason. Include, well, you always need that in case you need to compile native code. The lib directory will be just for stuff that's part of the implementation. There will be nothing in there that's intended for end user modification or direct use. And of course, in the lib directory, there will be a modules directory that has modules in some yet to be designed, yet to be determined, potentially highly, highly optimized internal form, maybe with AOT code and who knows what in it. But it's an implementation artifact, and we will reserve the right to change it at any time. So if you write code that depends upon it, that would be unwise. So rt.jar and tools.jar are going away. This will, hopefully this won't impact that many developers. It will certainly impact people who build tools and people who build IDEs. And naturally we will communicate the intent behind this well ahead of time. I'm starting to do that at this very moment, and recommend replacements for them. Okay, security. As I said, Java security has kind of been in the news lately. We've been doing a lot of work to make the platform more secure, to make its implementations more secure. It's been a fairly long road. What does security have to do with modularity, or put it a different way, how can modularity help security? Well, here's how. This is a list of all the packages in JDK 8. Now, many of these are things that you would actually expect to use. Look, there's java.net. Here's, java.time, new API, JSR 310. Some of these are APIs that they don't start with Java or JavaX, right? The ones that start with Java or JavaX are specified by the JCP, and they have to be provided by every conforming implementation. There are packages that don't match that pattern. So there's a JDK package that has some stuff in it. There's sun.packages and whatnot. And many of these packages have been around for many years. Some of the non-Java JavaX packages are actually intended for external use. So let's see, where's an example? I'm not seeing an example right now because I left some off. Anyway, there are some. For example, we have an HTTP server, a little HTTP server. It's not part of the Java SE standard, but it is part of the JDK. It's a documented API. if somebody's using it and they file a bug on it, we'll actually fix it. There's also a bunch of stuff here that's really just internal to the platform. One of the famous examples is sun.misc. Sun.misc has been around since even before Java 1.0. It has some stuff in it that used to be useful in many cases, is no longer useful because there are proper public APIs for them. Sun.misc does contain one incredibly useful thing called sun.misc.unsafe. How many people have written code that uses sun.misc.unsafe? Yeah, so you know about that very, very sharp knife. Sun.misc unsafe, among other things, will just let you peek and poke arbitrary memory addresses. So there's a fair amount of stuff in here that's internal. It's not meant for external use. And from a security perspective, is really tough to deal with because the Java language gives us no way of hiding them. Sun.misc unsafe gives you arbitrary peek and poke. It would be kind of a bad thing if a Java applet came in and was supposed to stay inside the sandbox, but manages to hack its way out of the sandbox, gets into Sun.misc unsafe, and basically has as much access to the system as it can figure out. That's not good. But the language doesn't help us here. The virtual machine doesn't help us here. What have we done about this problem ever? Well, the solution was to implement something outside the language in the VM. For those of you familiar with the security manager, it's called the check package access method. So this is a method that is supposed to be invoked by any code that does anything resembling reflection. So not just class.forName, but all the code in the reflection API, the method handles API. Turns out, well, that's actually a very fancy advanced form of reflection. And there are a variety of other essentially reflective APIs in the platform. So the idea here is that when code implementing a reflective API is invoked, it should ask on behalf of the caller, well, should this particular caller, whatever its code source is, does it have permission to access this package that it now wants to access? Now, this can work as long as every single code path in the system that's supposed to do that check actually does that check. But of course, there are many code paths in the system that are supposed to do that check. There's no way to validate statically that every code path in the system that's supposed to do that check does that check, really. And so this has, sadly, been a source of security vulnerabilities. We would really like to get rid of check package access if we can. It's brittle and it's error prone and just nasty to deal with. Well, guess what? If we have a module graph, we have a very natural way to solve this problem. If we've divided the platform into a big set of modules, we understand what their interdependencies are, then we can treat each module as something that can be encapsulated. We build a little wall around each module. It only exports to other modules what it wants to export. Stuff that's internal, it keeps internal. It stays internal. And it only gets to see classes and interfaces that are exported from other modules upon which it depends. It doesn't get to see other random stuff from some module way other, in some completely different part of the graph that's unrelated. So a module then can be defined not only by the packages in it and the dependencies, which are the arrows, but also the set of its API packages that it exports. Or if you want to be really fine-grained, we could actually list the specific classes that it exports. And also, some modules are, the entire module is internal. And we actually want to limit which other modules can link to it. So a module could say, well, I'm an internal module, and I only permit foobar and bass to link to me as long as they're part of the system. So encapsulation is, like Lambda, a very old concept in computing science. Here we are. Let's use it again in Java. Obviously, Java already has encapsulation in several forms. Let's add a new form of it that's centered around modules so that we can improve the security of the platform. Now, Another side benefit of this is we can improve the maintainability of the platform by hiding internals. Some of those internal packages I showed you, they're not particularly security sensitive, but they're painful for us to maintain. Historically, those of us who've maintained the JDK all these years, we have tried hard not to break these unsupported APIs because and it's sometimes been really hard. Not because it's particularly technically burdensome, but it can just be a lot of work, right? That we have these unsupported APIs. Developers have over the years written libraries that use these unsupported APIs, and many other developers have gone and used these libraries, so they don't even know that their whole application depends on some unsupported JDK-specific API. They're just using this handy library. So out of sympathy for the developers who have unknowingly depended on internals, we generally do fix bugs in unsupported APIs. We have no sympathy at all for people who write libraries that use these internals. None. Don't even ask. So there's no gain without pain. There's no gain in making the platform easier to maintain without imposing some pain, and that's going to happen when we modularize the platform. Sun.star packages, any package with the name internal in it. Internal is a package naming convention we introduced quite a while ago now. It's meant to be kind of a hint. If a package name has internal in it, then you probably shouldn't use it. But of course, people do. And we've gone and looked. When my colleagues downloaded all of Maven Central about a year ago, and did a scan of all of the artifacts, and found a shocking number of libraries, some of them very popular, that they just happily reach into sun.blah.blah.internal.blah.blah, and it's like, okay, well, sorry, you're going to break. So this, forewarned is forearmed. It's now is an excellent time if you're a library maintainer to go look at your libraries and consider whether there are things you should fix. And if you're a library user, to maybe ask the question, am I using libraries that are depending on these things because I'm going to need them to get fixed if I want to run on top of a modular Java platform? So 3 big goals: improve scalability of the platform, improve the performance of the platform and also applications, improve the security of the platform, and along the way, let's improve maintainability, because in some ways it's almost the same problem. I work for Oracle. And we have 23 minutes for questions. Thank you. The handy Twitter tag is at the bottom. If you'd like to ask me a question via Twitter, please do. But please mention M. Reinhold. I don't have a search set up for the tags. If you're not shy, there are microphones you can use, or you can just talk, and I'll try to repeat your question, but I might get it wrong. Question is, what about classes from the JDK that use Sun MISC unsafe? Well, of course, special provision will be made. There will be an edge in the module graph that allows whatever module that class is in to access Sun MISC unsafe or whatever replaces it. So yeah, that's not a particular problem. Interesting thing about Sun MISC unsafe is, and this might sound a bit alarming, Sun MISC unsafe has now been around for a long time. It's a de facto standard, right? Every time those of us working on the OpenJDK implementation change it, we always touch base with our colleagues at IBM, because J9 supports all of Sun MISC unsafe too, because a lot of stuff depends on it. It's time to make Sun MISC unsafe an actual standard API. So don't be surprised to see a class called maybe Java Lang unsafe in a future release. But it will, of course, have lots and lots of security fences put around it, because it's not just for random use. Yeah. Let me see if I can repeat the question. If you're going to use modules, then you can't use class loaders. Is that correct? No. No, you can still use class loaders. It depends on which classes you're loading, right? If you're using class loaders in a way that will only load platform classes or classes from your application that you gave to the linker, then well, it'll find them. It'll be happy. If you used a class loader to load some platform class that you don't have or some application class that you don't have, well, it's going to fail in all the usual ways it's going to fail. So there's no real problem there. I'm sorry, there was a second part to your question? Can you still use the service provider API? You mean that Java util service loader? That's just resource lookup. Resource lookup has to continue to work. So yes, that should still work. Most things will still work. Services are interesting. We're not clear on whether services are something that the module system should know about or not. In our first prototype, which was built around some requirements that aren't really relevant anymore, services are very much part of it. Right now, not totally sure. I'm just scanning the Twitter feed. Oh, good. People are repeating the message. Do not use sun-internal packages. Thank you. Here's a question. What about logging warnings when an app unknowingly uses restricted packages? So the user actually knows this. Yes, that's an excellent idea. In fact, we implement it in Java C and Java 6. If you run Java C without the secret magic flag that turns off the warning, and you try to compile code that refers to sun misc unsafe, it will tell you, no, you shouldn't do that. It'll still do it for you, but it will tell you that you shouldn't do that. Can you publish a list of libraries that will break with Jigsaw? No. Why not? Well, A, it's not a short list. B, we may be, all-seeing, all-powerful Oracle, but we do not have access to every piece of Java code in the world. So, we just don't know. Could we publish a list of popular ones that we happen to know about? Well, aside from potential libel suit exposure, yeah, we probably could. Maybe we will.
You already did the analysis and could spare all the developers using them to look up themselves?
Yes, we have already done the analysis. We will no doubt refresh the analysis a couple of times before we're done. And yeah, we could, maybe public shaming would actually motivate people to go to fix their libraries. So, yeah. What's the fate of modulareinfo.java and I would say the more important part of the question is what about modularity features for use outside of the JDK itself? So that's actually a question for you, I think. Insofar as there is clearly there needs to be something that you would call a module system in order to modularize the platform. Is that something that you, folks in this room, would want to use yourselves? Yes? No? Yes? Okay. No? Don't care? Okay, fair enough. And then the follow-up question is, well, which parts of it are you most interested in? What would be your primary motivation? Hiding internals. Security. Modularity, motherhood, and apple pie. Sorry? Give me the linker. Okay, working on it. Okay, yeah.
You have blocked that you think it's not necessary to support multi-version modularity. I assume this is okay for the platform itself. But I assume if more libraries are being used and things get more complex, it would be very useful to have that. Thinking about a Java EE container and things like that.
Right, so let me see if I can summarize the question. I know the issue very well. The question is first there's an assertion. I have blogged that I don't think it's important to support multi-version modularity, and in some sense that's true. So what about complex application scenarios where you need multiple versions of a particular module in the system. So one observation to make there is that most applications run in a fairly simple way. If you built an application that expects a class path, and there are two versions of the same component on your class path, that's a bug, right? The class path just doesn't work that way, and your code is probably going to fail in some bizarre way when you get a class from the new version trying to talk to the class from the old version, and it's really hard to debug because you just get these mysterious class def not found errors, and it's incredibly painful. So most applications, I think, are already written on the assumption that there's only one version of anything. Even in the EE case, if you look at a well-written EE application, whether it's just a web app or something more complicated in the whole ear thing, there's a very specific way things are loaded. There are still class paths in there, and it is still a bug if there's more than one version of something. Something will go wrong, practically guaranteed. Now, if you look at the bigger context of a Java EE container or any kind of container thing, look at Eclipse. Well, it's basically a big container, right? If you look at a bigger context of a highly dynamic system into which a lot of code is dynamically loaded and unloaded, then yes, it's perfectly sensible to consider that, well, in say, Glassfish, Glassfish will need its own XML parser. It's going to use some XML parser, but maybe some EE app gets deployed into this instance of Glassfish that it just needs a different version of the XML parser, so it carries it along with it. And so now from a global perspective, yes, here you have a system that's got two different versions of JAX-P in it, or two different versions of JAX-RS or JAX-WS, whatever. Yes, that's true from a global perspective, but that doesn't mean that you need a module system necessarily that can handle arbitrary mixes of multiple versions of the same named module in an arbitrary kind of graph. This kind of duplication happens in a very constrained way in something like an EE app server, and we think we know how to make sense of that and support it, even though in the kind of obvious approach to the model, well, no, if you're writing an application, it's just a bug if you need more than one version of anything. So that's my perspective on that. Let me do a quick skim of Twitter here. Server flag. It will cause use of internal classes to throw a throwable. Yes, indeed, an excellent idea. We're contemplating that. In addition to the Java C flag I mentioned earlier, actually not flag, the built-in warnings that you can disable with an obscure undocumented flag, in JDK 8, in preparation for modularization, we've added a new command line tool called JDEPs, and I expect the IDs will eventually cotton onto this and provide a graphical interface. JDEPs is a tool you can point at an arbitrary jar file, and it will tell you what platform, what JDK classes it's using, and it will tell you which ones are internal. So you have a very easy way to scan arbitrary binaries, including those handy libraries you downloaded from Maven Central, to figure out where all the bad kids are. Let's see. Okay, I'm not seeing any new questions. Peter, I think you had a question?
So how does the modularity relate to, say, launchers, like JavaFX launcher? Like, does the JLink help with that?
So how does modularity relate to application launchers, in particular the JavaFX launcher? Can modularity help with that? Indeed, it can. You know about the JavaFX packager? You can think about that as a prototype for JLink, right? Once we have JLink, or whatever it winds up being called, the JavaFX packager can just be a script that turns around and uses JLink to do those transformations.
I mean, that the original presentation where you were demonstrating RPMs and stuff like that.
So are you referring to the dependency management aspect Right, okay, so a little bit of background. We've been working on this first prototype of Jigsaw, you know, on and off for well, many years now. Jigsaw actually started as a project at Sun Microsystems, old company you might have heard of, in 2008. Some of the requirements on Jigsaw at that time were motivated by Sun's desire to get into the feature phone, the smartphone business, and build a Java stack there. And one of the requirements for that was basically to be able to do dependency management, to do something akin to, you know, RPM or Debian packaging. Because if you're trying to build a smartphone platform, you need a way to, you know, to download different bodies of code and relate them to each other as modules and figure out which ones are missing and download those too, and you do all the provisioning stuff. So this was part of the first Jigsaw prototype from the beginning. Now, dependency management, you know, if you've looked at how this problem is solved, well, it's actually a really hard problem. You know, we had a fairly naive solution to it. We started working, in fact, Paul Sandoz, sitting right here, started working on a much more sophisticated solution to it. You know, the right solution to dependency management is to go use what's called a SAT solver, which is, you know, basically a sophisticated set of heuristics for solving a Boolean satisfiability problem. And you can get an optimal or near optimal solution to a dependency management problem by transforming it into a SAT problem, running a SAT solver, and then translating that back into an optimal or near optimal graph of dependencies. So there's this whole, you know, area of rocket science that's just around dependency management. You know, Maven took a stab at it. Every build tool has taken a stab at it. You know, RPM took a stab at it. You know, Debian took a different stab at it. You know, it's a hard problem. There's no great solution yet. As we were coming back to the Jigsaw project after taking some time off to go fix a bunch of security bugs, we took the time to, you know, consider all the requirements that had guided the first prototype, and among other things realized, you know, we actually don't need to solve this dependency management problem. We can rely on existing tools, you know, Maven, Gradle, Ivy, whatever your favorite is, to go figure out what artifacts you need. You know, download them if needed. Maybe download a bunch of other stuff that you don't need, but, you know, that's not a problem. In terms of what we're exploring now, in, you know, what we've started as a second prototype effort, we want to rely on existing tools as much as possible to do dependency management. So certainly you know, there will be a module system that has a concept of a module graph. There will be modules that relate to each other and say, you know, this module needs that one and that one and that one in certain ways. What we would really like to do is only be in a position of validating those dependencies. We will check that everything you need is there. We'll check that there's nothing extra. If you give JLink, you know, two different versions of the same module, it will immediately say no, try again. If something's missing, it will say no, you know, go edit your POM or whatever to get all your dependencies down. And once they're all there, it will validate that and do the graph computation. But the dependency management game it's just not a game we think we need to play anymore. So in a way, it's a big relief because it's a huge amount of work to do that right. Yeah.
If you build a module for one application, I can understand that you can build a smaller runtime environment for your application, which is good for small devices. But my experience is that you most of the time end with 10 or maybe more applications. So will the delta of those applications then not be a lot bigger?
It all depends on your situation. Let me see if I can repeat the question. So if you build your application as a module, then it would have enough information in it to tell you exactly what parts of the runtime you would need in order to configure a minimal runtime. But then if you're in an environment that has a whole bunch of applications, it could be the case that if you do the transitive closure of all of those, that you'll wind up needing a big chunk of the runtime or maybe the entire thing. Well, yeah, that's true. But I think that's just a consequence of the particular set of applications you have. There's nothing modularity can do to help you.
Yeah,
I mean,
if they build it as one application and then they put the other application next to it, isn't there a risk that you duplicate the runtime environment?
if you build one application and then you put another application next to it, isn't there a risk that you would duplicate the runtime environment? No, I don't think so. I mean, you'll have the runtime. It'll have whatever modules are in it. You'll have one application running on top of it. If another application comes along, if everything it needs is in the runtime, great, it wins. If something's missing, then eventually something goes boom, and you have to cope with it. So there's no duplication of the runtime. There's no attempt here to say, oh well, we're going to virtualize the entire runtime for every application. That's an entirely different kind of solution, which is interesting, but that's not, I think, what modularity is about. Yeah, let's take this offline, please. I want to give other people a chance. Yes, sir. I didn't mention OSGI in any way. That's true. Where is OSGI in this picture? So OSGI is useful for some things. It's this big, rich framework, as you may know, there's a module layer and a security layer and a services layer and a lifecycle layer. And if you need all that stuff, it's great. Go use it. But guess what? Most applications don't need all that. So our intent around OSGI has been clear for many years. OSGI, whatever the modularity solution in Java turns out to be, OSGI has to run well on top of it. And there are certainly opportunities to expose things from the platform's module system into OSGI to make that story smoother. And in fact, there's another project in OpenJDK called Penrose where some folks are exploring exactly how to do that. So OSGI is important. It's very useful for a small percentage of applications. It has to run well on top of whatever the solution turns out to be. But OSGI, for a variety of reasons, can't be the solution itself. Somebody who hasn't asked a question. No. You already asked a question. Okay, let me check Twitter one more time. We've got 4 minutes left. Here's a question. Can we already try Jigsaw and Lambdas with JDK 8 snapshot? Well, no, Jigsaw's not in JDK 8, so it wouldn't be there, would it? Could Jigsaw modules ever replace the EJB module web module structure in Java EE? Quite possibly. We've spent a significant amount of quality time with people from the EE team, understanding both how the EE spec thinks about class loaders and modules, and also how implementations like Glassfish and WebLogic Server and others think about modules and similar concepts. Let's see. Okay, I don't see anything else new here. So another question in the room?
May I?
Ooh, using the microphone. Yeah. Thank you very much.
Okay. Is the Gmod, are they vendor lock, or you can use some of the Oracle, some of other companies, when it will be implemented by everyone?
I'm sorry, could you repeat? I just couldn't parse that.
Okay, so you have module done by Oracle at the moment, and when it will be done by other companies, the dependency will be a mix between different implementation, or?
If you could you have? Are you asking the question? Could you have modules from different vendors that relate to each other and work well together? Absolutely.
Exactly.
Yeah, totally. Sure.
Okay. Thanks.
Yep. My phone is buzzing. Somebody's learning lots of interesting things. Good. How does ProGuard relate to JLink? I have no idea. I don't even remember what ProGuard is. I've heard of it. Obfuscation. Oh. Yeah, whatever. Never grokked the point of that. Oh, well, yeah, insofar as it removes useless code, there is some similarity to JLink. Obfuscation of itself is just kind of silly. Yes, sir, near the back. No, near the back. Would we consider horizontal class extensions in modules? I might if I knew what a horizontal class extension was. Adding extra methods. No, I don't think so. even separately from modules. Adding extra methods, small talk is there. Have fun. That doesn't feel like Java to me. There was someone else in this.
Are the DE containers going to benefit with this first implementation of Jigsaw, or will they end up always loading all the files anyway because of the spec?
Will Java EE containers benefit at all from this first implementation of Jigsaw, or will they wind up loading everything anyway, just like they do today? Well, that's up to them. We're very serious about working with everyone who builds and maintains one of these things to understand what their requirements are and figure out how a platform standard module system can help them. But we obviously don't have the ability to go convert every existing app server in the world to use these facilities. One last question I think we have time for. Yes, sir. Will there be a notion of versioning? That answer to that goes back to my answer to Peter. Yeah, modules probably need versions, but versions are essentially part of the whole dependency management game. If there are versions in modules, then yes, we will certainly validate them and tell you when there's a version mismatch. But if a version that's required isn't available, then all of these tools I've been talking about will just issue an error message, hopefully a helpful one, saying, sorry, don't have the right version of this. Go edit your POM or your build file or whatever's appropriate. Okay, we're out of time. Thank you very much for your questions and feedback.